Hi, my name is Andrew McLaren. Today we're going to talk about friction in a couple different levels. We're going to talk in general about when we have friction and when we don't, a little bit about normal force and how it's related to friction, as well as friction's actually on slope and how that actually works into a lot of problems, and the difference between kinetic and static friction explained, as well as an example of them in a problem. Okay? So when we're talking about friction, it's really useful to consider when we don't have friction, like when we're on an ice rink. And I would like you to try and imagine someone trying to run on an ice rink. It's very difficult because there's basically no friction. You could put like a very small amount of friction, so they might be able to get accelerating a little bit forward. But a lot of times in physics, we'll say something just doesn't have physics when it's got a small amount. It just makes the math doable. And you can kind of imagine that like in this situation where someone's trying to pull this box, if there's no friction here, this box is just gonna get sliding along as fast as they can honestly pull on it. So as long as they can apply that force applied, they should be able to get some acceleration. And then if we think about like, okay, well, let's think about maybe you're on a basketball court. Now the ground actually does allow you to have some friction. So with friction, you are able to actually get running a little bit easier. And that means like there's actually a force friction here. Um, that's significant, and it's like a big size in our force diagram, indicating that it should cause a good amount of acceleration, right? You can also see these forces have canceled out. Realistically, this force friction should be smaller than a force normal because these don't get bigger than that. It's just kind of their relationship, or it comes from their relationship. So you can also imagine with a basketball court, now you're going to have to overcome that friction that's on the ground. So you might have to pull harder on this box to get it moving due to there being friction. So yeah, you may be able to run faster, but it's going to be harder to get things moving as well when you have friction. And then I wanted you to imagine, like, let's say that we're on a road and it's a much bigger friction now that you can have on that road. So you can actually get going faster on these rough surfaces. That's why cars will kind of spin out on roads. That if they don't have good enough traction, they'll spin out. But if they do have good enough traction, they can maintain that friction and they can get going really, really fast. But you actually need the road to have some traction as well. So you can't put like these speed cars on like ice rinks or things that just have no friction, um, because for those types of vehicles, that won't really help them get acceleration. So we kind of know what friction is or how it affects us. Like if we have too much friction, it's kind of hard to move or like get something to slide across that. But really what friction is it's how hard it is to slide due to how much these forces are exerted on each other from these two different objects. So if you've got like the ground exerting some force on a box, like a force normal, they'll have a hard time sliding past each other. The box also exerts a force on the ground, which is the equal and opposite force. So these two have that force interaction between each other, and so we have this friction here now. And so you can imagine if you have kind of like a zoomed in look at what this looks like, you've got the object on the top and the surface on the bottom. There's some interactions, and these molecular interactions are what causes that friction. But the easiest way to really think about friction and to really grasp it and how it relates to this force normal is to think of a book that's just on a desk and think about how much friction it has if you try and slide it sideways with some force applied. Um, there's going to be some friction. And in the y direction, it's not going to be going up or down because the normal force and gravity, they've canceled out against each other. And this is why it's important to say that friction is not due to gravity. It's not that simple. It's due to the normal force. Because if you push down on a box, you've increased how much force down it's experiencing with that FH, is how I've written it there. And you can imagine that also now the force normal has gotten that much bigger. So this force normal has to get proportionally a little bit bigger to cancel out that negative number. So now there's got to be more friction. And this thing's going to actually have an increase of friction compared to beforehand. And same sort of deal here is like, okay, well, now if I lift up the box, if I try and lift it up a little bit and kind of slide it, if you've ever tried to move like heavy furniture, this is kind of what people do, depending on if they're sliding it. So in this case, there's an even smaller force normal because that force H is already canceling out some of the gravity, aka there's not as much contact between the surface and the object. And so in that case, because you've got a smaller force normal, you've got a smaller force of friction. And there is a whole formula for the force of friction, which relates to these two variables. So there's this one variable which could be like 0.1, maybe 0.5, or like 0.9. It goes from 0 to 1, the value of this guy. The coefficient of friction is what they would call this, which is going to be the force of friction over the normal force. And so you're basically saying like, okay, the force friction could be as much as the force normal, but not more. And this is going to be like a very like rough surface that has those high values of friction. And these are going to be smoother with lower values of the coefficient for friction, because that means there's a smaller force of friction for the same normal force. So that's a way of mathematically describing what we looked at with these books and thinking about the normal force. It really is how much contact these two things have, and that's going to cause these interactions. So it's very common for you to see physics problems on slopes, and they might have some friction, and you oftentimes need to relate that friction to the kinetic motion. So maybe the acceleration of the block. So you can see in this problem, this is a great example of how you would need to use force friction on it. And force friction is always perpendicular to the normal force, so they always are 90 degrees from each other. So the force friction should be along the plane of the surface, going sideways along that surface, and the force normal just goes like straight up from that surface. So just keep that in mind, is like these things are 90 degrees from each other, and that's how you set them up on this type of problem. And then you oftentimes need to like cancel out force friction with some other vectors. In this case, it's just force of gravity in the x direction. And so those guys are canceling out. And there's no acceleration here. So you could solve for this force friction just with the force of gravity, which you could get from the mass here. It is interesting to note, though, that you could solve for the force normal from the f of gy. And if you get the force normal, you should be able to get this coefficient of friction as well. So like it is basically saying like, okay, we have these two pieces of information. We should be able to get the kinematic, or in this case, this is actually the static friction because this object is still. So this should be for the static. And we're going to talk a little bit about the difference between kinematic and static friction. They're very, very similar. One's motion, one's staying still. So when we're talking about friction, there's two main types. There's when an object is still and when it's moving. And when something's moving, there's actually less friction. So if you look at this little drawing that I've got here, the two sides, because they've got like some bits that can kind of fit in each other, those are going to hit each other and moving sideways. So a object that's already moving actually is a little bit further away from the surface that it's sliding across, just because it needs to be. Instead of like going up and down, up and down, up and down, it just goes over the hill and just kind of keeps on gliding along that way. And so there's less friction when you have kinetic motion than when you have static motion, which means that for everything that I'm aware of, when you look at the values of its kinetic and static friction, the static is always bigger than the kinetic for like that value also. So this could be like, oh, if an object is still, maybe it's 0.5, but if it's moving, maybe it's 0.4. So like it's got less friction once it's moving than when it's still, which kind of makes sense if you've ever pushed an object. It takes a little bit more effort to get it moving, but once it's actually moving, you have to overcome less friction. So kind of makes sense in that regard. Now you have to be careful with these things in math problems because a lot of times they'll do this tricky thing where the friction that you're calculating is often like the maximum friction that the object could have. But if there's less than that being applied, the force of friction could actually be less. So for example, in this problem here, there was I think it was in part A or 8, you were able to realize like, oh, like this object, it needs to have, or it had a force max of 6.2, but it actually only needed 3.27 to stop the motion in the x direction. So it's kind of like a maximum value that you could get, but it isn't actually that force of friction. So you could have an object that you're pushing, but you just haven't pushed it hard enough to overcome this force of friction. And it will just cancel out. Like this object isn't going to be moving in the direction of the force friction. Like it's not like a negative thing here. These guys just cancel out in the x direction. This force friction and this force that's being applied in the x direction. This tension, I think, in the x direction. So you gotta be careful a little bit because oftentimes the force that you're talking about is maximum, but in the calculations you gotta be a little bit more careful with that. In addition, there was a couple situations here where it's like, okay, well now you have more force and you've overcome that force friction. Basically, if we look here, it looks like the sum of forces was not 0, or was it actually equal to 0 in this problem? Give me a second to review this. Actually, it looks like in this situation, the F max could only go up to 4.9, and we had, in this case, no, the tension was only going to go up to 4.9, but the force friction could go up to 5.5. So it does actually cancel out in this case as well. But then there was a little bit of math that I did here, seeing as like, okay, this almost canceled out at 6, so it's just a little bit more. And if you do a little bit of math, you can actually see that this would overcome the force of friction at 6.589 newtons. So we're almost at the point where we're overcoming that. And then you could actually calculate some acceleration. If they said like, oh, now you have 8 newtons of force, you could relate that and find the actual acceleration. Thank you for McLearning with me. Before you go, please check out the following services that I offer with my business. So if you click the link in my videos, this goes to my website. I might be changing it from Podia because I'm no longer doing the interactive videos for sale. I might put those up for free. But most of my other services are linked here. So you can see that I've got like a Teachers Pay Teachers and a Wyzant. The Teachers Pay Teachers has a lot of my assessments that I have for like the NGSS, as well as lessons that I made when I was actually a teacher in the classroom. So I've got quite a few things like CERs and other things on there. If you want to get one-on-one live support from me, either like with science or like working on like teaching support lessons and that kind of stuff, you can sign up through Wyzant. I have a link to there where you can contact me there, and we can schedule hourly appointments. And I've got a few other things on here like a Facebook page and other social media. And if you're interested in getting professional development with me for like a team of teachers, a whole page with information on that. So yeah, feel free to check that out. Thank you.